Welcome everybody, my name's Connor McDonald. I'm a database advocate for Oracle Corporation. Now the title, From Bitbucket to Extreme Performance. What exactly do I mean by that? It means this: as IT professionals, we always have ideas. We'll be doing something mundane like walking our dog, and all of a sudden an idea springs into our mind. Something that's going to be a fantastic application, something that's going to take the world by storm. The problem with these ideas is you have an idea in January, and often the time it takes to get that idea into something, into fruition, into a real solution, is a huge amount of time, and all of that represents lost opportunity. Ideally, we want to take our idea from the moment we have it and literally, in the case of maybe minutes or hours, have a website up and running. It might not be the fully fledged product, but at least we have the ability to start getting people interested. We're starting to sow the seeds of this idea into the world. So we want people to be able to join up, register their interest, etc. We want to get that idea up and running as soon as we can. The problem is the number of lines of code we have so far is 0. And that's a problem. That's going to obviously take time. What we really need is just some mechanism of storing data. As long as we can get people interested, have them register, we just need some persistence. We don't need too much rigor at the moment. And the perfect model for that is JSON. Very flexible, very easy to take from, say, a JavaScript application, grab some JSON and just store it in the database. And to store it, literally, it's just a few lines of code if you're using something like Soda. So very, very quick from idea to a website. And if you want, obviously, you don't even need to do any hardware. You simply grab one of our cloud services and you're off and running with, say, autonomous JSON. Now the time frame from idea to website is almost 0. And the great thing is, as your idea evolves and you start getting more ideas, you might want to change your website. You might want to take some surveys of customers, or they even might want to participate in, say, a beta. This rapid style evolution is also very easy with something like JSON, because the JSON is very flexible. You can simply evolve it over time, store whatever you want as your application sort of goes from Genesis into something that's going to be a little bit more realistic. And the cool thing is, even though it's JSON, as you start collecting this information, if you want to start doing trend analysis of it or start looking at stuff in a more relational fashion, it's easy with some of the JSON features available. So you can simply dump JSON and still get some sort of relational facilities out of it. Eventually, though, you want to actually start taking people's money. And that's perhaps a bit of a time where you might want to step back and think, well, this application has gone from idea to something that's real. It's a financial thing. It's a commercial activity. Now's the time we might want to actually look at adding a bit of rigor. The problem is the jump from just storing any information that comes from my website into a relational database structure with rigor and all the great properties of relational databases, it's a big jump. All of a sudden, I've got all this DDL, etc. to write. I've got a lot of properties to understand. That's a big jump from just storing JSON. The great mechanism we have for doing that, to make that jump easier, is a thing called QuickSQL. You can go to quicksql.oracle.com. You notice you actually can create a relational database structure in the same way that you would actually store your JSON. It's just a nice hierarchy there. I'm going to have some customers with some various details. Those customers are going to have some orders, and each order will have some items, and those items will consist of various products and quantities. I pretty much just lay it out almost in the structure I have with my JSON. And QuickSQL does the heavy lifting of generating all the DDL required to build that relational structure. That's going to be our starting model here. I've finally taken my application, I've added a little bit of rigor, I've used QuickSQL to build a convincing data model. So this is what QuickSQL built me. It gave me a customers table with some attributes, it gave me a product categories table, it gave me some products, it gave me an orders table, and you can see the primary keys and indexes are all being built for me. It gave me an order items table, it put all the foreign keys on, all this stuff came out of QuickSQL for me. This is your first logical jump when building applications and moving from, say, JSON to a relational structure. Don't get me wrong, that is a great model. I'm not saying this is something that you would just start with. This is a really good model, and you can do industrial strength applications with this. That's fantastic. What if, though, your idea was one of those great ideas that actually became a worldwide hit. You've suddenly gone from a commercial application to something which is now an absolute global blockbuster. You can hit what we call a success crisis. A success crisis is when your application is literally so incredibly successful that you might now need to take that next step in terms of relational theory. And this is one of those sad moments where people have these things called success crises, and rather than stepping back and looking at their relational model, they race out and they start writing blog posts saying, oh yes, we hit the limits of relational theory, we have to move to some other platform, we have to introduce huge amounts of complexity because relational doesn't scale. That is just complete fiction. Let's do a demo now with our starting model and see how good the database is just with what came out of QuickSQL. So just to show you, we're going to quickly run through the script that QuickSQL came out. It created us a customers table. It created us some products and put the various constraints on. We had an orders table, some order items, etc. This is what came out of QuickSQL. And you can see that QuickSQL has also enabled some basic auditing facilities for me. On each of the tables that are about to be created, it has added a created by column to track who created the row. QuickSQL also typically adds a created time as well. You'll see shortly that QuickSQL creates a trigger to capture those values in those columns. It also gave us our foreign keys, which is nice. It also handles things like surrogate keys, population of surrogate keys, all the things that you would normally have to handcraft, it takes care of for you. It created the sequences, gave me some triggers to populate the surrogate keys if they're left out, and the created by column is populated as well. One on customers, one on orders, one on order items. I'll put in some sample data there just to seed the tables to get going because I need some customers and products at least initially so that I can start taking orders against them. And here's our application, the ability to create a new order, create a new customer, add some order items, just written with some simple PL SQL procedures. And what I'm going to do is create a little benchmark application here which will let me stress test this data model. I've got a little table here called results which will serve two purposes. When I run my benchmark with multiple concurrent sessions, each one of them will record their elapsed time and transactions per second in the results table. But also, at the start of each benchmark, they will attempt to get a lock on this table or a row in this table so that I can control exactly when the concurrent sessions will all start. And here's a little benchmark utility I've written just in PL SQL. You can see two routines at the bottom of the code called init and run. Init will build up a list of random customer and product IDs to create orders. We use dbms random and the seed procedure to ensure that each benchmark will use the exact same set of random data to ensure consistency of results. We're going to place 40,000 orders, and every 200 orders we're going to create a brand new customer. We're simulating lots of activity. This benchmark will actually run in concurrent sessions. There's the rest of our benchmark, and when it's finished, we update our results table to actually store some metrics that we can then look at. So what I'm going to do now is lock my results table, and this will stop all my benchmark programs dead in their tracks before they start to make sure they all start together. I've launched off another 6 SQL Plus sessions here, all of which are now about to start our benchmark, which is going to slam away orders and customers as fast as it can. They won't start until I hit commit. Let's give that a go. Now this benchmark has now got 6 concurrent sessions, all literally as hard as they can, slamming away at this relational model to see how many orders per second I can place. Let's see how we go. And once the benchmark is finished, it will actually give us a summary of what those 6 little children did in terms of working their way through. And here's our summary. You'll see the other little slaves fall away and disappear shortly. So what did we get? On average, a slave took about 20 seconds to crank through our 40,000 orders. So we got about 11,600 orders per second. That's nothing to sneeze at. I read somewhere recently on Google that Visa processes around about 4,000 transactions per second globally. So if you can get 11,600 transactions per second, that is probably going to be fine for the vast majority of applications you ever build. But we're talking at the extremes here. I will note that if you stay with me and do the hands-on lab after this session, you won't see such high transaction rates if you're going with the always free database, because that's just a single OCPU database. But still, I think you'll be impressed with the numbers. This information here is some diagnostics as to where that time was spent. We burned a lot of CPU and we had a few other interesting things that we're going to tackle now. The first one here, we've got ENQ CQ contention and a whole lot of CPU time. Let's have a look at those things now. So the question that comes, if I can get an average turnaround time of 20 seconds and 11,500 transactions per second, can we do better? Triggers that we saw in our quick SQL are just extra code you put in your database, and obviously code consumes CPU. These are the triggers we have, and the reason they're there is to populate surrogate keys, because if the order ID is someone tries to attach null to it, we're going to force it to picking up our next surrogate key using sequence.nextFile. We had one on the orders table. The problem, the reason we have these triggers is due to this. Historically, if we could put a default on a table, like if the status comes in as null, I want to default it to n. If I don't nominate the status in my insert statement, that'll pick up the default of n just fine. But what this didn't stop was someone explicitly saying, I want to insert a null into the status. That's a problem, because when you did that, even though you had a default set, we would actually get a null in that column and therefore break our database or our data model. So that's where triggers came in to force that value, even if someone tried to put a null in there. But from 12c onwards, we've had more null control. Now, not just default, we can have default on null. So with those columns there, I've got a status, start date, commission, job level, etc. They've all got default on null, which means even if someone explicitly tries to put a null in there, we actually have forced the value of the default in there. With that information, we don't need triggers anymore to populate those nulls. So let's do the next demo now and see what benefit we get from not having those triggers. This will recreate the schema from scratch to make sure we have a common benchmarking baseline to work from. So our customers table, our product table, everything's in there as before. Notice now I've changed the defaults. Default on null to the sequence value. So I don't have to have triggers because default on null will take care of that for me. Order items the same, default on not on null user. All the things that originally I had triggers for are now I'm just using default on null. Constraints, etc. And all the trigger code is now commented out. I no longer need the trigger code in there. The rest of it is the same. Seed the data, create my application, create the benchmark table, create the benchmark. I lock my table in exclusive mode so all the slaves will start at the same time, and we leap straight into it. So once again, all our benchmark slaves absolutely hammering away. Our first benchmark was 11,500 transactions, about 20 seconds of elapsed time. Now that I've removed the triggers, I'm hoping to see some benefits. And here's our result. I've gone from 20 seconds, I shaved off a few seconds, I got down to 18 seconds of elapsed time on average, and I've had a nice little boost in transactions per second. I've gone from 11,500 to about 13,000 transactions per second. That's an excellent result. Most of my time was once again spent using CPU. That's a good thing. We want to use CPU. That's what we pay for. But here's the things we're trying to now eliminate. We've got a thing called ENQ SQ contention and some buffer busy waits. Let's now see if we can tackle them. ENQ SQ contention is when we have contention for sequences. Now, caching is a facility of sequences that's meant to handle that. And what happens is people think that caching is going to be an expensive operation. But in reality, sequence caches are not cached. Let me explain. When I do create sequence my sequence, it says we have a default cache size of 20. People think that because we have the word cache in there, that what I've done is allocate 20 pieces of memory in my SGA for all those 20 sequence numbers. Therefore, I wouldn't want to do something like sequence cache 1,000 because that would consume 1,000 pieces of memory. That is not how this caching works. When you create a sequence, we store a thing called the last number. That is the last number that is going to be stored in the dictionary, and the rest of the numbers can be cached up to our cache size. So when I do a select sequence.nextFile, you'll see that number bumps up to 21. What we're saying is that I can now allocate the sequence numbers 1 through 20 from memory without having to update this data dictionary table. It's that data dictionary that causes the contention. If I have high frequency transactions, orders, order items, etc., there is no memory cost to having a high cache, and it alleviates that dictionary contention. The second thing I want to talk about before we do another demo is what I call the myth of foreign key indexes. Once again, there are numerous blogs out there that say if you don't have an index on every single foreign key column, your database will collapse and die. This is not true. The rule you need to be looking at for an Oracle database between a parent and a child relationship is, do you mess with the primary key? What do I mean by mess by? It means, do you update the primary key? Do you change it? Or do you delete the parent rows? If you do that, you probably need an index on the child table. If having that index on the child table helps performance in its own right, then obviously that's a no-brainer as well. If one of those two things is true, then you need the foreign key index. But if not, you don't. In our data model, if I have customers to orders, am I going to delete a customer and therefore delete all their orders? Probably no way, because financially I'm not allowed to do that. I would probably mark them as deleted, but I wouldn't delete the row because that would remove the order rows from my database. However, if a customer comes in, they're probably going to say, show me my orders, which means it makes sense to have an index on the customer on the orders table. So in this case, this is a foreign key index I would probably keep. If I'm coming in from product to order items, will I ever delete product? Once again, probably not, because it would wipe out all my order history. I'll have a flag that says it's no longer available. Will I come in on the product index for order items? Probably not. I'll probably come in on the order ID. So this is a case where I might not need that foreign key index. So let's run another demo now with a better sequence caching and removing of foreign key indexes we don't actually need. Once again, we'll clear out the entire schema to give us a consistent base for our benchmark. Now you can see the caching I've done on the sequences. Only bumped up the customers one to 100, it's not that high frequency, but for our orders, I've gone up to 2000. Why 2000, you might ask? There isn't a hard and fast rule as to what the cache size should be, but since I'm getting around 10,000 transactions per second, a cache of 2000 means I'll be updating the dictionary about 5 times per second. If I continue to see SQ contention, I can just bump up the cache even more. The rest go through as unchanged. I'm keeping this index on the orders table for customer, as we saw in the slides, but I'm not going to keep this index because it's very unlikely I'm going to ever need it for performance or locking perspectives. Of course, this doesn't stop me from doing queries by product. They would just be full table scans. And if I'm doing something like sales per product per year, then a full table scan is probably the best option anyway for scanning large volumes of data. I roll through the rest of the constraints, insert some seed data, there's my benchmark, and off we go. Let's see how we go this time. You remember that without the triggers, we got to about 13,500 transactions per second and about 18 seconds elapsed time. Now we're making great strides again. I've gone from 18 seconds down to 11 seconds of elapsed time, and now I'm getting 20,700 transactions per second. You can see I've eliminated the ENQ-SQ contention issue. Let's pause for a second here. That's about an 80% improvement on our first benchmark. Often you'll hear of companies spending huge sums of money on hardware upgrades just to get maybe 10 to 20% improvement. And if you flip this around to the world of cloud, then this would mean you could run the same workload for about 80% less CPU, and that directly maps obviously to savings for your business. Now, the two elements that are stopping us from getting closer to our utopia of 100% CPU are buffer busy waits and NQTX contention. Buffer busy waits are often contention for table blocks in memory, and ENQTX contention is contention for common blocks in an index. Table block contention can manifest itself in many ways, but a first step to treating it is by distributing table blocks more sparsely, and I'll use partitioning for that. Index contention brings us onto the topic of ascending index keys. So let's go back to the slides. Can we do better? Ascending keys, we're using sequences for all of our surrogate keys, and ascending keys can sometimes be a bottleneck when they're being used in indexes. An index is stored as a tree-like structure, and they grow from left to right in terms of ascending sequences. So if every single index key is slightly higher than the previous one, we get contention for that rightmost leaf block. That can be an issue. That can slow down the ability to actually accept transactions. What I can do is hash partition those indexes. And as a result, I'm spreading the index load over multiple physical segments on the disk. The DDL looks something like this. I simply say I'm going to partition it by a hash on the primary key column. In this case, I've nominated 4. That would give me 4 logically distinct indexes, physically different segments on the disk. Therefore, the contention has been spread out over 4 different leaf nodes, and I could make it 8, 16, etc. Let's do our final demo to see if we've managed to improve one more time. Clear out the entire schema. Everything now is kept as before, the caching as before, tables as before. Now you can see in our definitions, I've actually chosen to partition my orders table to spread out the load across the table. I am doing that to alleviate the buffer busy waits, and partition the orders index to spread out the load across those index leaf blocks. I'm trying to scatter workload across the database to improve performance. Same with the order items, and you can see I'm using a slightly different syntax here for the index. The using index local tells the database that the index will be partitioned in the same mechanism as the parent table. So order items and its primary key are both hash partitioned. And now everything else is before, and let's rerun our last benchmark. We're cranking it through. We got to just over 20,000 transactions per second last time at about 11 seconds elapsed time. We're hopefully going to squeeze out a little bit more here. And yet, we just tipped over the 21,000 transactions per second mark at about 11 seconds of elapsed time. Our first demo was about, I think, 11,000 transactions per second, so we've just about doubled it just by making changes to the physical design. But look at that CPU figure. In our benchmark, 99% of the elapsed time is pure CPU. That is ideal for us because we're getting the maximum performance that the underlying hardware can deliver. And it's also a strong indicator that if we needed more performance, then a CPU increase would actually assist. Don't get me wrong, we aim for CPU to be the dominant component when our SQL code is already well-tuned and optimal. If you've got bad SQL, then that can also get a server to 100% CPU, but that is definitely not the aim. In extreme cases, people often even partition their tables across various rack instances to get, once again, bigger jumps in terms of performance. But as we can see here, getting to 21,000 transactions per second is probably going to handle 99.9% of applications in the world today. So let's wrap it up. As I said, what you get out of Quick SQL is a great data model, and good is often good enough. 11,000 transactions per second is probably going to accommodate the vast majority of applications out there. But if you manage to stumble across one of those ideas, which is the absolute superstar idea that is going to be incredibly high transaction rates, then know how to make the jump to that great level. That's the key thing. Okay, hopefully you enjoyed these demos. Let's jump into some Q&A. If I don't have the partitioning option, are there other options available? Yes, at the very pointy end of performance where we explored partitioning in the demos, if you don't have the partitioning option, you could look at reverse indexes, which flips the bytes in index keys as they come in, once again trying to spread the load across multiple parts of the index instead of the leading part. The other one is a thing called scalable sequences. Scalable sequences perturbate the sequence number a little bit such that multiple instances and multiple sessions will once again try put indexes or index keys into different parts of the index to avoid that contention on the leading blocks. What about sequence gaps with high caches? Okay, let's put sequence gaps to bed once and for all. If you're using an Oracle sequence, the potential for gaps is always present because the moment you grab a sequence number to use in a transaction and roll back that transaction, let's say someone tries to insert a value for your orders with a negative quantity, that sequence is lost forever. There is always that opportunity that sequence numbers should go missing. They are generally meant to be just meaningless surrogate keys. Unfortunately, we know auditors can get a little bit upset about those kind of things, but there will always be some gaps. The other place where you might get gaps is when a sequence is aged out of memory. And if you have a massive cache size, then all those numbers will be lost. You can work around this by using the package dbms shared pool to pin the sequence in memory. And that point, doesn't matter what the cache size is, they'll be the chances of gaps are the same as before in terms of a transaction rolling back. But the faster you can get to a point where you don't care about gaps and sequences, the happier place you'll be in. What about sharding? Where does sharding fit in here? Okay, the examples we saw today were effectively just running on a single instance database. We can scale that further by going to something like Rack, where we have multiple instances against shared storage. We can take that to the next level by using something like sharding, which is multiple sets of those clustered or unclustered databases all combining to form a logical single application footprint. You generally need a few application implementation and design level changes to achieve this, but other than that, all the hardware and communications and comms is taken care of for you. That's a big difference from some other database vendors where if you want to shard, you pretty much have to manage the whole thing yourself. But sharding is that next level in terms of performance if you want to, for example, have geographically disparate systems and still present a single logical application footprint. With the changes you did throughout the demos, can QuickSQL do all of that for me as well? As we saw, QuickSQL gives you a very good baseline set of attributes and tables for performance. One of the key things I'd recommend is in the settings section for QuickSQL, you can nominate what version you want to generate your tables for. The more later version you choose, the more opportunities QuickSQL will take to take advantage of those features. I think out of the box, we probably support things like 11G, 12, 18, 19. So we sometimes will choose the lowest common denominator to make sure it's going to work across the board. But yeah, if you can tweak the settings in QuickSQL to say, look, I'm generating this for a 19C database, for example, it'll do its best to take advantage of all those potential features. I don't think it's going to use things like partitioning off the bat because it doesn't know if your system is licensed for partitioning. You mentioned that triggers were a cost overhead, and I've read that Tom Kite says that all triggers are bad. Do you agree? Tom Kite, my predecessor, used to be famous for knowing that he said he doesn't like triggers at all. I'm not that severe on them. However, I do think when we use triggers to implement things that we could do declaratively, like default on null, etc., I think the trigger is generally going to be a bad option. Because if you can keep that mindset of, can I do it declaratively and therefore not use a trigger, you also avoid things where we often use triggers to implement things like foreign keys or uniqueness checks. And generally, that's where you can get into all sorts of grief with triggers when you're trying to implement things which are across sessions. You need a lot of locking concerns to make sure they are just right. If you can steer clear of that, then using triggers for their intended purposes, simple augmentation of existing functionality that can't be done declaratively, I think that's a better way of thinking about triggers, and you'll end up with probably less of them and make your code base easier to manage. Is that a bit? We use triggers to add the auditing columns you mentioned. Are there any other ways of doing that and not having the triggers? Yes, there are. Look at something like Flashback Data Archive or, for example, fine-grained auditing. Both those things have a particular way of working, so they might be a fit for you, they might not be, but I'd always stress that look at the features available in the Oracle database because there's so many, it's hard to keep track, to see if you are not reinventing a wheel that has already been invented by someone else. I know some of our internal applications we're using for our code implementation are using Flashback Data Archive as a mechanism of journaling changes over time, as opposed to using conventional audit triggers, etc. Bye for now, everybody.